All right, welcome back, everybody. This is William M. Briggs, and we're continuing our class on uncertainty and probability theory, the logic of science. Today, episode 20. Probability is not limiting relative frequency. And I want to make sure we understand exactly what I mean by that. It is not limiting relative frequency. We'll talk about the difference between limiting relative frequency and relative frequency as we get into this. And the importance of it is that absolutely no one, even those who profess to be frequentists hold with this definition of probability. Nobody, even frequentists, believes it. Nobody ever acts like they really believe in limiting relative frequency. And I'm going to prove that to you many times. Many times. I'll prove it to you today. I'll prove it to you again and again. Wait till we get to confidence intervals and p-values and things like this. Absolutely no frequentist ever treats these things as they should treat them in theory if they really believed the theory. And why is that important? It's not just important because somebody's making an error, although it's always nice to correct our intellectual mistakes. It's because of what they do with these theories and how they apply them in real life and make decisions with them. And those, of course, turn out to be tremendous blunders in science. The replication crisis, for instance, is driven by all this, in large part, not entirely, but in large part by, slavish devotion to wee peas and all this kind of a thing. Now, before we get to that, I want to thank Greg Glassman. He sent me this book, this wonderful book, Do Not Erase, Mathematicians and Their Chalkboards. And it's just a collection from a photographer of a bunch of chalkboards of mathematicians. I don't know if you can see this. I'm pretty bad about holding this stuff up. Terence Tow's. This is my favorite. He's got the twin prime conjecture there. He's famous for that kind of thing. And of course, what mathematician doesn't love thinking about prime numbers and everything? Well, that's a lot of fun. And of course, here's our chalkboard. So let's return to it. Now, this is the definition of probability in limiting relative frequencism. This is it. We have some event. It has to be an event now. We're thinking of events A. And we have some sequence into which we can embed this event. And we look at this sequence. And we count the number of times that A obtains. And we divide by the number of times that we've observed this sequence. And we take the limit as n goes off to infinity. And this becomes the probability. This is the definition of probability. In other words, what this requires to be a frequentist is omniscience. Think about it. I'm saying I don't know any probabilities. I don't know any probabilities until I observe a limiting relative frequency of events, an infinite sequence of events, of which I count the number of which have obtained this particular definition, some proposition of interest right here. That becomes the probability. Only then do I know the probability. Before I reach infinity, I don't know the probability. This is going to become the objection, the basis of many objections of why I don't believe probability is limiting relative frequency. We'll discuss those a little bit more in detail in just a moment. But now I could one thing I want to make clear. So why do people just go off on this and then they go to town and they have all this math about probability and so forth? Books and books are written on this stuff. Well, I could define this as some p, some mathematical object p, and then I can go to town with this. I could say, well, imagine I'm doing this 20 more times and I can come up with a binomial or something like this. Speaking of p, accepting p, conditional on p, conditional on assuming these probabilities. That's how I'm able to take all these textbooks examples and so forth and say, assuming I know the probability, and then I go off to town proving all these theorems. That works. They're all conditionally true theorems. There's nothing wrong with the math. I want to stress this again and again. I don't have any truck with the math. There's of course, mathematicians rarely make mistakes, but not as often as other scientists and so forth, just because of the way the science is conducted and so forth. So that's not a problem, but it's when we apply this math to real life, when we try to apply it to science, when we try to apply it to real life propositions of interest A, that's when we go wrong. That means if we're applying this math to real life, it becomes some sort of a model, it becomes some sort of representation of our thoughts on certainty. We have to make sure we understand exactly what we're doing philosophically. It's the philosophy of limiting relative frequency that I don't think is true, and I think is absolutely false, for the number one reason that we have to be omniscient. In order to know any probability, we have to know every event that will happen until the end of time. That's what infinity means. Infinity, we throw away, it's very easy to work with mathematically, as I've said before, but thinking about infinite thoughts and applying them back to our relative, not relative, but our finite discrete existence is a very difficult thing, and we're too glib with all this. Now, I can have evidence such that I can have E equals, there's 10 Schmengies in a room and 5 Minyaks, and of my proposition of interest is A, a Schmengi walks out of a room, walks out. Now this is a relative frequency, so I can have the probability of A given E is going to be, well, it's going to be 10 out of 15, so 10, 15, no problem. This is a relative frequency. So probability can certainly be relative frequency, or that is to say, the numerical result can be relative frequency. This is the relative frequency of Schmengi events to Minyak events. All right, no problem. But probability itself is still the relation between these two propositions, which we learned last week. We learned many weeks. These are subjectively chosen, but this becomes completely rigorous, this object itself, and it just has this numerical calculation, which we took great pains to prove that probability could even be a number in its functional form and all this kind of stuff. These guys just jump right to it. They just define probability as this. Okay, so let's get into more precise criticisms. I'm going to be basing this off of my book here. I'm going to read you some of these things. I'm going to erase this. I need to have some board space, and there's people somewhat agree with a lot of these criticisms too. I'm not going to say that they don't about probability being limiting relative frequency, and sometimes we shorten that to be just relative frequency or just frequency. So we got to be very careful. I just showed this example I erased, that probability can be a frequency. It doesn't have to be, but it can be, to defining it as limiting relative frequency, which is what people generally mean. In other words, we have to be careful about our notation, we have to be careful about our language and so forth. Well, there's this guy, Alan Hayek. I'm not certain I'm pronouncing his name properly, and if I've mispronounced it, I hope he will forgive me. I list here, he's got 2 papers, and I'll list some others. I'll put them up on the notes. They'll be down here, and they'll be in the lecture notes. Of von Frosten, he's got some mathematical objections. I'm not going to go through those kind of things about Borel subsets and all this kind of a thing. Technical criticisms of limiting relative frequency that are of interest if you want to be complete about this, but I'm more interested in the philosophy of these things, so we'll stick with that, and I'll provide you a link to those things. Meanwhile, we're going to go through some of Hayek's objections. So we just did the, I gave you the definition of it right here. So here's the thing. Of course, we have to know an infinite sequence. In order to know anything, we have to be able to embed our event A in some infinite sequence of events. And it can't be finite. We can't chop it off up here. We can't chop it off here. We can't chop it off anywhere. It has to be infinite, because that's the definition. If you don't like that definition, well, then you change the definition to something else. But if you're going to make the definition limiting relative frequency, you can't chop it off anywhere. So we might have, there's all kind of objections we can come to in here. This particular subset here might converge to, say, P1. This particular subset of this infinite set might converge to P2. The whole thing might convert, it might be out here to some incredibly high number. Let's do a tetration of 10 to the 10, tetrating to the 10 to the 10. Remember how we did those tetration kind of a things? This is an enormously big number we can't think of. All of this can converge to some P3, whereas this out here, if we were to add all of it in the entire sequence, might converge to some P4. We don't know, because we're never going to get to the end. And we're defining probability as what happens at the end. There's all kind of limiting theorems and rates of convergence theorems and the like. How fast does this probability converge to its true value and things like this? But all those hold conditionally by assuming the form of the probability in the first place. All right, all of those theorems assume the form of the probability and say, here's what happens when we observe finite sequences of them. So they're again conditional theorems, assuming the probability is already known and trying to back out what it looks like in real life. All right, we're going to meet this again when we talk about estimation and the like. But basically what it means is we've observed up to this point for some very large n, even for a large n, we've observed this sequence up to here. The limiting relative frequency says this stuff out here, if this stuff is going to converge to the true value, if this P3 is getting closer and closer to the true value, whatever that true value might be, it sort of implies, not sort of implies, it absolutely implies this remaining part of the sequence, which is how big? It is infinite in size. This infinity of stuff we never get to observe is somehow containing or constraining or is influential on this finite portion that we did observe. It's mixing up causality. It's mixing up the idea of causality. We know that real things cause events. That is to say, there are real causes and real powers and all this kind of a thing, which we're going to, actually we don't know. I've only sort of waved my hand on these ideas. But we are going to discuss all that in great depth of causality and so forth, and how we bring cause to probability. We don't get cause from probability. It's a delicate topic which we're going to spend quite a lot of time on. Important because we're using all of these hypothesis tests and Bayes factors and all these kind of things to decide whether or not cause has happened. It just doesn't work that way. It doesn't work that way in life, although in the math people say it does. So this is an objection here. It's subtle. Infinity is just too big. In any sequence, if you study analysis, we have an infinite sequence. There will be inside this infinite sequence infinite subsequences. All right, so we're going to have another. Let me try to. It's impossible to visualize, of course. Here's our sequence going out to infinity. And suppose here I've got a microscope or a telescope, I'm standing way back. This is an infinite subsequence in our infinite sequence. This, again, can converge to some P1. This infinite subsequence here can converge to P2, and they're not equal. And in fact, that's guaranteed. It's guaranteed. I have infinite subsequences in an infinite sequence, all of which I can group together to come up with different probabilities. I don't know how, I'm sure I'm not conveying that properly to you, but the idea, again, if I truly have an infinite number of things, an infinite number, that just goes on forever and forever and forever, I'm going to be able to look inside that sequence. I'm going to be able to take an infinite subsequence of them, and taking infinite subsequences of infinite sequences is done all the time in mathematical analysis. I'm going to find infinite subsequences in that entire sequence that converge to just about any number in 0 to 1. So how do I know that I'm over here, Mr. Finite, that this particular thing if I'm using this to make an estimate of the true probability, how do I know it's anywhere near all of these? And the answer is, of course, I can't. It is impossible. I can assume a form of probability. It takes some particular mathematical form, and then I can say, here is how this particular sequence, finite sequence, will converge to the infinite sequences if probability has a certain form. All right, I can give you a rate of convergence to all that, but that is assuming what the probability looks like in the first place. What if I don't know? If I don't know, then there's absolutely no guarantee that this particular finite sequence, well, it'll resemble, of course, it will resemble at least one of these infinite subsequences, and in fact, it will it will look like an infinite number of these infinite subsequences, because infinity is just too big. I could have a whole collection of, I could have an infinite collection of infinite subsequences here, all converging to something that looks like this, and I could have another collection, infinite subsequences, of an infinite subsequence that converges to something that's not like that at all, and so on. This should be somewhat exasperating to you, because I'm trying to define probability as what happens when I finally get out here at the very, very limit. And I'm saying that's what the probability is. And I'm saying that's absolutely false. People fool themselves into that because they use regular frequency, and there's nothing wrong with that. We've done that many times ourselves, and that works. And so they assume it must work at the limit. There's absolutely no proof it works at the limit unless you bring the assumption of what the probability looks like at first. That's one of it. I have a whole bunch of these, in particular, objections and so forth. Of course, if we had real-life events, say, I think I have basketballs being, a number of orange basketballs. I don't know what it is. Out of the sea of all the basketballs that exist in the world, some are orange, some are not. I've seen all kind of colors, green and white, and I remember back in 1976, they were red, white, and blue. All these kinds of things. So there's orange basketballs. So now I need to envision some sort of causal event. And I'm going to grab out one of these basketballs somehow, ignoring how, out of the sea of basketballs, and I want the probability that one is orange. Well, for logical probability, it's no problem. I just count or I estimate. I don't have to have probability being a number in logical probability even. We'll talk about that next time. And I can get an estimate for the probability that the thing is orange given whatever assumptions I make. For the frequentist, he has to imagine some way that there will be an infinite number of basketballs of any color, of all colors. And if there were, of course, that's the entire universe would be filled with basketballs. That's what infinite means. There would be an infinite number of these things. We would never be able to apply probability until we had an infinite number. We would never know the probabilities until we had an infinite number of these things. The entire universe would be filled with nothing but basketballs when we create these problems for ourselves. So it can't be done. So probability cannot be limiting relative frequency. I did all that. Well, I'll read you Hayek. This is quoting him now. For each infinite sequence that gives rise to a non-trivial limiting relative frequency, there's an infinite subsequence converging in relative frequency to any value you like, which we just did here. Indeed, infinitely many subsequences. And for each subsequence that gives rise to a non-trivial limiting relative frequency, there is a subsequence converging in a relative frequency to any value you like, and indeed, infinitely many subsequences and so on. Well, that's what we did. That's exactly what we did right here. It just can't be done. We would never have any knowledge of probability whatsoever if we required probability to be limiting relative frequency. As I said, we can always assume probability is this functional form. Probability is going to be, some function I could write down. I can easily do that, and then I could say, well, how is that going to behave in real life if probability is this? I could do that, but that's not to say I have some sequence some finite sequence that I've observed, and now I'm going to say, what's the real probability of that? I can always assign it. I can assign probabilities to it like this, and then do math. But that's not the same. That's cheating. That's if you're a limiting relative frequentist, that's cheating because you're assigning it up front. You're saying, here's the probability. Now I can do some math. I'm saying, no. All we have in front of us is this sequence. A finite portion of this infinite sequence into which you must embed your events. And so that's David Stove's objection. And the entire half of his book, the second half of his book that we've talked about before, The Rationality of Induction, this is, it's unfortunately, it's nicely titled, and it's inaptly titled too. The entire second half of this book, this is why I want you to read this book, is logical probability. The entire second half of the book. He spends the first part of the book discussing why induction is rational. We did all that in the first weeks of the course. And the second half of the book discussing why logical probability is the only sensible interpretation of probability. And I'll give you two objections right here. And I used in this book, we have a proposition of interest. And I didn't know it at the time, but I'm going to change it to the real life one here. So Kamala Harris wins the presidency. Now, von Mises, who was one of the guys who originated limiting relative frequency, he said, for me, such events, such singular events have no probability. They have no uncertainty. They cannot be put into probabilistic terms. But I think probably all of us can understand there's some uncertainty to this. Therefore, it would be nice to be able to measure it. There's no problem with logical probability doing so. We would say the probability that Q is true, given some evidence, is either some number depending on the evidence, or it's just going to be, either high or low or whatever we want depending on the evidence that we assume. We could do this in logical probability. But if we want to be frequentists about this, if we want to be consistent with the theory we avow, we have to embed this in a sequence, an infinite sequence. Every event has to be embedded in an infinite sequence. That's what limiting relative frequency means. So what do? All presidential elections, all with all just with women. In democracies, so-called our democracies, only in democracies. What? I mean, into what is this embedded? All countries? Only the USA? What? There's no unique definition for this to be embedded in. It's absolutely ununique. The reason why people like limiting relative frequencies, they claim it's completely objective. Whereas in logical probability, we have admitted there's a partial subjectivity. The partial subjectivity is, of course, in picking these items right here. Limiting relative frequentists allow the subjectivity of putting this part of the equation. They will just write this. They will not condition it on anything. And the reason they don't is because they believe it is a real physical quantity in the world. All right? So it is a real physical quantity in the world. It exists. There's a true value. You'll hear them speak of true values all the time. True values of this thing. And they want to either estimate it or they want to do something with it. In order to do that, we need to have a unique, it has to be unique sequence into which I can embed this particular proposition of interest. None of these are unique, and I'm sure you can think of all sorts of other possibilities for the sequence, for this sequence to be embedded in. Each of which would give us, as a logical probabilist, a different probability. But for the limiting relative frequentist, he has to come up with the probability, the true value. And that can't be done. It just cannot be done because there is no absolute sequence into which I can embed this. And that sequence, of course, has to go on for an infinite amount of time in order to know what this true probability is. Okay, that's one possible objection. We can't come up with unique. We cannot come up with unique sequences into which we can embed any observation. The other is, for limiting relative frequencies, they only want to speak of events in the world. So let me put it this way. I want to make a I'm going to come up with a proposition here. I'm going to come up with a proposition A. If USA not in World War I, no World War II. And I want the probability of this with respect to some evidence that I might do. This is a perfectly sensible question. Of course, it all comes down to the evidence that I'm going to assume here. And as we learned last week in proving that probability is not subjective, there's all kinds of ways I could define this particular E right here. It depends on how much knowledge I have of world history at the time and the minds of the people making the decisions and all this kind of a thing. It's a perfectly sensible question, though. And I've seen debates in England between... Oh boy, my mind is absolutely blanking. If I try to remember, I'll put it in the class notes right here. A debate, one of these Cambridge-style or Oxford-style debates, you know, it was a good thing America and Britain went into World War I. And of course, I think it was an absolute disaster. But hey, maybe your opinion differs. But I can answer that question. You and I can have a serious disagreement about these counterfactuals. This is a counterfactual. It didn't happen. Therefore, I can't embed it in any kind of a sequence. It's an impossibility. It is a logical and physical impossibility, both ontological and epistemological impossibility, but yet it still makes sense. I can still calculate probabilities with this, but not the limiting relative frequency. And of course, I can have all kinds of sequences, like I have 10 blue unicorns and 1 white unicorn, and one is going to pass by this tree, and I want to know it's going to be white. Given only this information, of course, I can calculate the probability is going to be 1/11. No problem. But for a limiting relative frequentist, this doesn't exist in the world. It is absolutely impossible that it's going to have any kind of embeddable sequence, let alone infinite subsequences of this kind of stuff. So they can't calculate probabilities based on this. Of course, people do. People who call themselves frequentists, they have no problem answering these kinds of questions. Banks, for instance, have no problem with counterfactuals. They say, I can't give you a loan because if I do, you probably won't pay it back. And so they don't give you the loan. Now, how can they check? They haven't given you the loan. They can't compare their model of you. Well, there's difficulties there. But counterfactuals, people understand these counterfactuals in real life. We have no difficulty understanding the uncertainty in them. And so do limiting relative frequentists. They have no difficulty understanding either. But they should. It should be impossible for them, because limiting relative frequency demands what probability is. But nobody sticks to it, okay? Nobody. Absolutely nobody sticks to it. It's just wrong. It's absolutely wrong. It's false. And I'm going to give in the notes below. I'm going to give you the excerpt from my book, and I'm going to give you some at least one other paper that you can look at if you're interested in the hardcore mathematical objections and things like this. You can peruse those to your delight. That's it. This, again, we're going to meet limiting relative frequency again and again, because of hypothesis testing, all these kinds of ideas and statistics and so forth. Next week, I think what we're going to do is we're going to, haven't made up my mind. I'm going to try to prove to you again that probability doesn't have to be a number, but I think we kind of kick that around so much, maybe you're already convinced of that. Let me know in the comments if you want to talk more about that, or maybe we'll just continue going on. We have a lot more to get to before. We haven't even got to bad science yet. We haven't even got to this broken science stuff. We're still building up our world here, and we're 20 episodes in. All right, that's it for right now. Leave questions down below or at the websites. The information will be listed right here, and I will answer them in next week's lecture. I don't have any homework except for to do the reading. But that's it for now, and thanks very much for listening.